So we're going to start out today by talking about speed, given velocity vector. So car A's speed is defined by the points -3, 8 and 6, 2. In other words, the black vector. Car B's velocity is defined by the points -4, 4 and 2, 0. So the blue. So B's blue. All right, Josh. Let's say you go to college. You get a job in Los Angeles. I'm still back here in Omaha, which is where I want to be or where you want to be. On the same day, we are traveling north at 55 miles per hour, but I'm in Omaha and you're in Los Angeles. I got two easy questions for you. Are we going the same direction? Are we going the same speed? Sure. Does it matter where we are? No, because that's not the description. That's not the properties of what we're talking about. We're talking about direction, speed. As long as you're doing the same, it doesn't matter where you are. As a matter of fact, you can't be in the same place unless you're riding with me, I suppose. Which would be fine. I'll give you a ride. I'm fine with that. So the point is, it doesn't matter where the vectors are. They have speed and they have direction. But we don't say they have, but the speed is length. Because it says which car is going faster. So which car is going faster, A or B? In this case. Which vector is longer? A, right? So who's going faster? A. A's going faster because the velocity vector is longer. So the longer the vector, that represents how fast this object is moving. So that's the whole idea behind vectors. It shows you how fast something's going and what direction it's going. How much faster? This is notes to me more than anything, because sometimes I'll make notes. I'll hand them out one year, go look at them the next year and go, why did I write that? Why do I have this slide? This is a note for me. All right, so we're going to find the component form. And the reason we can find the component form is it doesn't matter where these vectors are. They can be anywhere. So we'll find the x component and the y component. And we can do that by subtracting. So for A, the x component is 6 minus -3. That's 9. What does 9 mean? A, 9 comma something. And when we do components, we don't use parentheses. What are those things? Parentheses? Yeah, quotation marks, parentheses. All right. We use chevrons to indicate that this is a component form. So what does 9 mean? To go from here to here is 9 units. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's horizontally. X is horizontal. Y is up and down. How do we find distance? We subtract. 2 minus 8. You always do head minus tail. Always head minus tail. So that's -6. So from here, over 9, we go down 1, 2, 3, 4, 5, 6. Well, now writing the component form means what I've really done is taken this vector, and now it's at 0, 0, and the other end is at 9, -6, because it doesn't matter where it is. It doesn't matter. It has direction, has magnitude, or length. All right, so now vector B, its component form, is 2 minus -4. That's 6. So to go, let's see, 1, 2, 3, 4, 5, 6. Yeah, it's 6 over. And 0 minus 4, that's -4. That's 4 down. Now we've taken this and we moved it here by putting it in component form. So now we want to know how much faster is A going than B. So how do we find the length of those vectors? Not a trick question. How do we find the length of those vectors? Duncan? Distance formula. What's the distance formula really? What is it? Pythagorean theorem, right? Is it the Pythagorean theorem? That's what we need to do. All right, so it's a Pythagorean theorem. All right, so A's velocity. We're talking about velocity now. Now, how do we find, not velocity, I'm sorry, speed. We have the velocity vector, and if we want to find the speed of it, we do the Pythagorean theorem on it, which is called magnitude when you're doing vectors. Square root of 81 plus 36, square root of 117. That's A's speed, right? B's speed Square root of 36 plus 16, square root of 52. So we take square root of 117 minus square root of 52. I mean, who cares what it is? That's the process. It's some sort of decimal value. But that's how much faster A is going than B. So the whole point of this is when you're asked to find the speed in your homework, it is the magnitude of the velocity vector. In other words, the Pythagorean theorem on the velocity vector. Not the position vector, not the acceleration vector. There's three different types of component vectors you'll be dealing with. You go to that velocity vector to find the speed. That's the point of slide number 1. My computer crashed. I went back and copied the story problem again, but I didn't get these problems, so I'll just look off of here. Number 5, it says, find the magnitude of the vector in the direction angled theta it forms with the positive x-axis. So we have this vector 2, 2. So 1, 2, 1, 2, 2, 2, right there. And we can make this triangle. This is 2, this is 2. Here's our angle they want. What do they want? Magnitude first. Square root of 4 plus 4, square root of 8, 2 square root of 2. We just talked about finding magnitude. It's a Pythagorean theorem. But now how do we find the angle? Tangent of the angle we're looking for is 2 over 2. In other words, tangent's always y over x. So to find the angle, we just do inverse tangent of 1. We know that 1. It's pi over 4 or 45 degrees. So we know this one. I don't like 6 because it's almost the exact same problem. But let's say 6 was the point. Let's go with 2, negative 4. No, that could be a half. Something weird. About 2, negative 8. We don't know that one. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. This would be the vector right there. It has magnitude, it has direction, it has all kinds of stuff, and we want to find the angle. So we want to find, it would actually be, it'd be this angle right here, because we're in the, this is inverse tangent we're using. And the principal values come from fourth quadrant. So it's always y over x. So it's really the inverse tangent of negative 8 over 2. So whatever inverse tangent of negative 4 would be. I don't know. That's not a known one. So that'd be a calculator problem. You could find the radian answer for that. You could find the degree answer for that, depending on what your calculator is in. So the whole point is to find the angle, you do inverse tangent of y over x. To complete the problem, it would be 4 plus 64, square root of 68. Does 4 go in there? I think 4 does. 2 square root of 17. So there's your magnitude. Inverse tangent of y over x is what we use. And then as far as the 11 through 16, it says find the component form of the vector with the given magnitude that forms a given directional angle with the positive x-axis. All right, so 11, easy. That one's the easy one. Because you're at 1, 2, 3, 4, but at 180 degrees. So it's that vector right there. And they're asking, what are they asking? Find the component form of the vector with the given magnitude. Component form. I know this one. Negative 4, 0. No math needed. And then the magnitude is 4. It's 4 units long. See, it's not at an angle. When it's at an angle, then it's hard to tell. This one isn't. An angle of 180, and it's 4. 12. 270. 1, 2, 3, 4, 5, 6. Right there. So there's the vector right there. And the component form is 0, negative 6. And then the magnitude is 6. It's 6 units long. So when you're on one of the axes, no problem. Got it. What if you're not? What if you're at 5, 100 degrees? We want to find magnitude, the component form first, then the magnitude. Professors love to write this. Here's an aside. They love asides. That means it relates to what we're doing. It's not exactly what we're doing, but it relates to it. Thank you. She's really tall. Yeah. Unit circle. Pi over 3. What if we made this into a vector? What if we made that into a vector? The component form would be 1/2 square root of 3 over 2. That's what the component form would be. We know that. We know what the x value would be. We know what the y value would be. But we know that when the length of this is 1. Called the unit circle, 1 unit. What if it wasn't 1 unit? What if it was 5 units? Well, then it would be 5/2 5 square root of 3 over 2. That would be the component because it'd be out here, but all I have to do is multiply this times 5. There'd be 5 of those. Follow me so far? That'd be the point. To find the component form of this, we take 5 times, well, 1/2 is the cosine of pi over 3. Square root of 3 over 2 is the sine of pi over 3. So it's 5 times cosine of 100, comma 5 times sine of 100. That's how we're going to find the point, the terminal point. We know some values on the unit circle when the radius is 1, but what if the radius is 5? No problem. Just multiply times 5. So this is going to be a decimal. We don't know 100. We don't know. That's not a special angle of ours. What mode do I need to be in? Radians or degrees here? Degrees, right? How many are going to forget to change your calculator? All right, Abby. 5 times cosine of 100. Let's get an answer, even though it's a decimal. That's going to be negative 0.868. That would be the x-coordinate. And then 5 times sine of 100, I get 4.924, which puts me in the second quadrant where it belongs, because 100 degrees is in the second quadrant. X should be negative. So then we have 14 is the exact same thing. And then find the magnitude is just the Pythagorean theorem again. I don't think we have to do that again. And then 14, you have 13 cosine of 200, 13 sine of 200. There we go. Whatever that decimal value be, you can find the magnitude. I put a couple extra ones on here. Any questions on finding those? That's just a basic review. All right, let's finally get to a true calculus problem here. When you hit a baseball, boom, the position vector is v naught t cosine theta. V naught means the initial velocity. And then that right there is the y component of the position. So that's position up there. So we'll make a note of that. A baseball leaves a batter's bat at an angle of 60 degrees from the horizontal, traveling at 110 feet per second. A fielder who is standing in the direct line of the hit with his glove at a vertical reach of 8 feet catches the ball for the out. There's not a worse feeling in the world than just drilling a baseball and it goes right to the guy and he doesn't even have to move. That's a sinking feeling, like, wow, he didn't have to take one step. So he's just standing up here at 8 feet catching it. His feet do not leave the ground. He didn't have to jump. Find the position vector of the baseball at time t. All right, so letter A. Is initial velocity is 110. We have t, and then cosine of 60. So we started out with an angle we know. And then we have 110 t sine of 60 minus 16 t squared. And then we're assuming that literally the ball was hit right from the ground. Else we would have an initial height too. We'd have a plus something on there. But we don't. We're not going to worry about that. All right, we can simplify this a little bit. Cosine of 60, 1/2. That's 55t, comma 55 square root of 3t minus 16t squared, because the sine is square root of 3 over 2. 110 divided by 2 is 55. So there is your component vector at any time you want. You want to know where the ball is at 1 second, you plug 1 in. B. Find the velocity vector of the baseball at time t. Here's the good news. Just take the derivative. So 55 55 square root of 3 minus 32t. There's the velocity vector. At what time t does the fielder catch the ball, and how far is he from home plate? So let's take the first question on letter C. At what time t does the fielder catch the ball? So we know when someone catches the ball because we can visually watch them catch it. But what about mathematically? How do we mathematically know that we've caught the ball? Okay, I like that, but we're not going to use that in this case. But I like that answer. I love it. If this was regular equations, that's exactly what we would do. But this is a little different. And the reason I say that is you'd have to find out, if we wanted to use that process, we'd have to find out when this is 0 and when that's 0. Because we'd have to find out when both components are not moving. Well, that's never going to be 0. So that won't work. What else will work, though? The position is 8. Exactly. So what do we want to be 8? This? We're on the right direction. We're on the right path. What do we want to be 8? The y, right? The y to be 8. That's what I was getting after. We want the y to be 8. So we want 8 equals 110. Oh, I have the 55. I don't want that. I don't want the original. I want this piece right here. 8 equals 55 square root of 3 t minus 16t squared. So we can do this two different ways. We can minus the 8 over and find out when it's 0, or we can just set and find out when that equation is 8. So in y, now we don't know how to do this by hand, so we're going to use our calculator. 55 square root of 3 minus 16 x squared. I think I missed an x. Let's back up. Insert x. Enter. We want to know when that equation crosses 8. So we'll put 8 there. Now if we go zoom 6, probably not a great view of what's going on here. There's the 8 up there, but this is a parabola. I mean, that's how baseballs fly, parabolic, right? So window, how about 0 to 10? We're not talking about negative time, and maybe the ball goes up to 200 feet, something like that. This is probably a better window, which is not absolutely necessary, but it's always nice to see a nice graph. That seems more reasonable. Now, if I went up to 200, 8's going to be really low. Well, compared to 200, people are not very tall. So calculate, except for her. She's really tall. Intersect, enter, and then I'll guess somewhere about 5. And it turns out to be 5.869. 5.869. So we found the y component is height, right? Up and down. X is right and left. And how far, what time t does the fielder catch the ball? T equals 5.869 seconds. I better write a nice answer, a good answer, so I get a good grade. And how far is he from home plate? So now what are we going to do? X, right? What about X? What are we going to do? What are we going to do with X? Plug the T in, right? Plug the T into X. Because here's your horizontal position, and we can just plug that in. So here's the good news. If you used your calculator to find that value, X has that value in it. So you go to the home screen and go X times 55. There it is, 322 feet. So the other answer is 322.780 feet. All right, finally, letter D. And this is why I showed you the first slide for letter D. Letter D. How fast is the ball traveling when he catches the ball? How do you find speed? Magnitude of the velocity vector, right? So we're going to go back to velocity. But we have this variable in here. But we're evaluating this for letter D at that t equals 5.869. We have to evaluate. We got to get rid of the variable before we can find an actual value for the magnitude. So we're going to do square root of 55 squared plus 55 square root of 3 minus 32 times the 5.869 squared. That's what we need to do on our calculator. And the good news is x is still holding that value. So 55 squared plus 55 square root of 3. Whoops, let's delete that. Minus 32. Yeah. Times x squared. What'd I do? Oh, yeah. Delete. Square. Boom. Oh, great. I know what it is. It didn't like that thing right there. Delete. There we go. And square root of answer. Boom. So 107.648 feet.